Bismillahirrahmanirrahim. In this chapter or in this section, we are going to talk about methods of sample introduction and atomization. Here you can see a picture of the here you can see a picture of an atomic absorption spectroscopy equipment. You can see different parts of the instrument. The first part is a hollow cathode lamp. Then we have the flame. We have the monochromator, the detector, amplifier, and recorder. But in the lower part of the flame, you can see a nebulizer that is used for spraying the sample into the flame. You see a sample solution that is sucked by the nebulizer or pumped by the nebulizer into the flame, and this is what we are going to talk about it, the method of introducing the sample into the atomizer. This is a picture of a flame atomization instrument or equipment that you see. There is a beaker containing the sample, and there is a tube, a narrow tube that we call it capillary tube, and that we'll use to suction the sample and spray it into the flame. But we are going to talk about the structure of the nebulizer and to know how it works. Here you see that there are different methods for introducing a sample solution into flame or plasma. The most commonly used method is using a nebulizer, but there are other methods also, like electrothermal vaporization, via flow injection analysis, HPLC hydrogenation, and prop. Here in this table, you can see different methods that is used for the sample introduction in atomic spectroscopy, like pneumatic nebulization. That is the most common method, the most usual method that is used both for solutions and for slurry. Then we have ultrasonic nebulization, electrothermal vaporization, hydrogenation, direct insertion, laser ablation, spark or arc ablation, and glow discharge spattering. We will talk about them later. Here you can see what will happen with a sample that is introduced to the atomizer by nebulization. In the left side, we have a sample solution in a beaker. By nebulization, we will make the sample to very tiny droplets that we can call it a spray or a mist. This mist or this spray will introduce into the flame and it will be heated. It will be heated and will lose its solvent. To this step we say desolvation. So this step is called desolvation, or losing the solvent. Then we have a dry aerosol. By increasing the temperature, this dry aerosol will be converted to a vapor. So we have volatilization. We have a vapor of the molecules that were in the solution. And then by increasing the temperature again, this vapor will be converted to free atoms. It means that the bonds between the atoms will break and we will have separate atoms, a vapor, the atoms in the vapor phase. This step is called dissociation. So we have nebulization and dissolution, volatilization and dissociation. Of course, the free atoms are in equilibrium with molecules, and in a higher temperature these free atoms can be partly ionized, so they can be in equilibrium with ions as well. Okay, now we are going to talk about different nebulizers. The most common nebulizer is pneumatic or pneumatic nebulizers that use a gas like air or argon in plasma. As you can see here, samples are dissolved in an aqueous medium in this method and then introduced into the atomizer by means of a nebulizer that converts the liquid into a fine mist or aerosol. Here you can see two nebulizers that are the most common nebulizers. In the left side it's called concentric tube nebulizer, and in the right side it's called cross flow nebulizer. In the concentric tube we have two tubes that are in the parallel, and one tube is inside another tube, and in the tip we have a very narrow hole that the sample will be in this from this hole the sample will be pushed out and will be converted to very tiny droplets. This is called concentric tube. In the right side we can see another type of nebulizer that we have two tubes in this method that are not parallel, but they are crossed each other with an angle of 90 degrees. So the sample is coming up from down, and then from the other tube we have a high pressure gas flow that will flow the sample and make it to a spray or a mist. This is this is an animation from the a kind of nebulizer that we called it concentric nebulizers. In this nebulizer, as you see, the sample solution will be converted to very tiny, very small droplets, and it will introduce into the flame in this with this method. Here you can see the structure of a burner, that in the first part of the burner we have the nebulizer. So the nebulizer will introduce the sample droplets into the burner, and in the burner we also introduce a fuel and an oxidant, and then they will be mixed with each other, and these small droplets of the sample with the gases, with the fuel and oxidant gases, will introduce to the burner head, and then it will burn in the burner head. You should know that only very small droplets can reach to the flame, and other droplets, the heavy droplets or big droplets, will just go to the waste and they don't get to the flame. So only about 5 to 10% of the sample will go to the flame, and 90 to 95% of the sample will go to the waste and will not reach to the flame. We have two other pneumatic nebulizers. One of them is called fritted disk nebulizer, in which the sample solution is pumped onto a fritted surface through which a carrier gas flows. It produces a much finer aerosol than do the first two. The fourth one, and the number D, is Bobington nebulizer, which consists of a hollow sphere in which high pressure gas is pumped through a small orifice in the sphere surface. Liquid following in a thin film over the sphere surface is nebulized by the expanding jet of gas. In here you can see the pictures of these two nebulizers. In the left side you can see the fritted disk nebulizer. As you see, there is a fritted disk, and the sample solution from top will come down, and the flow of gas can make the sample a mist or very tiny droplets. In the right side also you can see the Bobington type nebulizer, that we have a hole or orifice that high pressure gas will come out of this orifice, and the sample is poured from top on this sphere, and then we will have the sample solution as a mist or tiny droplets again. These two nebulizers are not as common as the two first one, the concentric and crossflow that I said. The concentric and crossflow nebulizers are the most common types, but these two are also used, and especially these two nebulizers are appropriate for or suitable for high salt solutions. When you use, for example, sea water that is very salty, then this type of nebulizers are used instead of the two first nebulizers. We have another nebulizer that is very much more effective than the others. This is called ultrasonic nebulizer. In this one, the sample is pumped onto the surface of a piezoelectric crystal that vibrates at a frequency of 20 kilohertz to several megahertz. Such nebulizer produce more homogeneous aerosols than pneumatic nebulizers do. So this is a better nebulizer than the pneumatic nebulizer, and this is more expensive. And here you can see another picture of this type of nebulizer, and the red crystal, the crystal is shown by red color. You can see the crystal, piezoelectric crystal. The sample flows on the crystal, and the crystal is vibrating, so the sample will be converted to very small droplets, and this type of nebulizer is much more efficient than the others. Okay, if we have a solid sample, is it possible to introduce solid samples directly into an atomizer, for example, into a flame or into a plasma or into an electrothermal tube a graphite tube, for example, to analyze it directly. Here you can see that the introduction of solid samples have several advantages. For example, the pre-treatment and dissolution steps are not necessary in this case, and contamination of reagents is minimized. Dilution errors are eliminated and sample wastage is avoided. So, because we don't need to dissolve the sample, we just weigh the sample, powder, for example, and put it directly into the atomizer. Another advantage is analysis of the sample at the micro level is possible, reducing analysis time, improving detection limit, and reducing the cost of materials and personnel. So you don't have to spend time for making solutions or dissolve the sample. But how can it be possible? How can we introduce a solid sample into the atomizer? There are many different methods. 5 of them are mentioned here. These techniques take a variety of forms. 1. Direct insertion. One of the methods is direct insertion of the solid into the atomization device. For example, you can use a probe that you can put the sample on top of the probe and then introduce in the, for example, in flame. Second one that is very important is electrothermal vaporization. That's called ETV, electrothermal vaporization method. In the electrical vaporization of the sample, we transfer the vapor into the atomization region. So we use electrothermal vaporization to evaporate the sample by heating, and then the vapor will be introduced to the atomization region. Other methods are arc and spark or laser ablation of the solid to produce a vapor that is then swept into the atomizer. So we use arc, spark, or laser to evaporate the sample. Another method is slurry nebulization, in which the finely divided solid sample is carried into the atomizer as an aerosol consisting of a suspension of the solid in a liquid medium. So in this method, we don't dissolve the powder, we just suspend it in the solution, mix it, vigorously mix it hardly, and then we have a suspension of the sample, and this suspension can be introduced into the atomizer, for example, by an ordinary nebulizer. Another method is sputtering, that is only used in a glow discharge device, and we will talk about it later. Because electrothermal vaporization is a very important method, I have explained something about this method. As you can read in this slide, it is an evaporator located in a closed chamber through which an inert gas such as argon flows to carry the vaporized sample into the atomizer. A small liquid or solid sample is placed on a conductor such as carbon rod or tantalum filament. An electric current then evaporates the sample rapidly and completely into the argon gas. Here you can see a picture of this method. In the left side, as you can see in the picture, we have a carbon rod or graphite. It has been called graphite platform. Then we have, by applying electricity, this graphite platform will be heated, and the sample is on the platform. So by heating the graphite platform, the sample will be evaporated, and then we have an argon carrier gas that can carry the sample vapor into the ICP, for example, in this case. Okay. Here you can see the arc, spark, or laser ablation. The ablation methods. This is the laser ablation method, that a pulsed laser beam has been used to evaporate the sample. We have here a solid sample, and then the beam of laser has struck the sample and evaporated the sample, and the sample vapor will be conducted to the atomizer by usually a flow of an argon gas. Here you can see the slurry sampling. As you can see here, we have a solid sample, and then we have added some diluent, for example, some water. And then we have used an ultrasonic probe to suspend the sample particles and make a homogeneous mixture. And then by using a probe, or for example a pipette, a micro pipette, we can pipette the sample and then inject it into the atomizer. In this case, the atomizer is an electrothermal atomizer, or electrothermal tube. This is a graphite furnace. Graphite furnace. We will talk about it later. Okay, here we are going to talk about dissociation and ionization. When the sample is introduced in the flame, one of the steps that we talked about it was dissociation. As I said before, in the dissociation step, the molecules will be converted into atoms in the vapor phase. So if the molecule is MX, for example, NaCl, or another salt that has been evaporated and it's in the flame, or a plasma, then this molecule that we call it MX will be dissociated and converted to M plus X. So we have here a dissociation constant that is equal to the concentration of M in the vapor phase, that we call it Nm. You see, Nm is actually is not the concentration, because concentration is used for solutions, but in the vapor phase, instead of concentration, we use N, that is the number density. So it is the density of the atoms. Instead of concentration, we use N. So we have Nm, then we have Nx divided by Nmx. This is the dissociation constant. For calculating the dissociation constant, we have an equation that's called Saha equation. Log of Kd is equals to this equation. The last part of this equation, the last sentence of this equation, is the most important one. That is 50/40 Ed divided by T. Ed is dissociation energy and T is temperature. So dissociation constant is proportional to T and Ed, to temperature and dissociation energy. But because a minus is before this last sentence, so it means that if Ed is smaller, then the dissociation constant is larger, the dissociation of the sample is more. And if the temperature is higher, also the dissociation will be more. So if for some elements that have less dissociation energies, for example, alkaline elements that have a smaller ED, for them we have higher dissociation. They will be dissociated more easily. And if we have higher temperature, also the dissociation will be more efficient. Other than dissociation, as I said before, if increase the temperature, we can have ionization as well. Some part of a metal can be ionized if we use a high temperature. So we have another equilibrium here, that M gives M plus electron. Here also we have a Ki, that is ionization constant, that equals Nm plus N electron divided by Nm. And we have a similar psi equation here, log of Ki. And the last sentence again here is the most important sentence, and we have E ion, that is the ionization energy, and T is the temperature. So if the ionization energy of an element is smaller, then we have more dissociation of that sample. And if the temperature is higher, also we have the same phenomenon. Okay, and then we will talk something about interferences in atomic spectroscopy. Let me stop here and record the other slides in another file, because I think this file will be too large otherwise. So interferences in atomic spectroscopy will be discussed in the next file. File. Okay.